Good morning, students. This is our third lecture on relativistic quantum mechanics. Today, what we shall be doing is we shall search for equations which remains invariant under Lorentz transformation, as well as that equation must describe the particles which move close to the speed of light. That means their de Broglie wavelength is compared to the Compton wavelength. Now let's make a little recap on the Lorentz transformation. It's very simple. You are used to this. These are the two frames. This is the S frame and this is the S prime frame, and S prime frame is moving with a velocity v, where v vector is v times x prime cap. So that means this is moving with a velocity along the x prime axis, and in this case x axis and x prime axis are coincident, and the usual notation is let me write down x0, x1, x2, x3, and x0 is denoted as ct, it is denoted as x, this is y, and this is z. Actually x is denoted as x prime, and here you have the coordinates x0 prime, x1 prime, x2 prime, x3 prime. These are the prime coordinates, and you have actually x0 prime is ct prime, this is x prime, this is y prime, and this is z prime. And the usual transformation which you have, the transformation is like this. The t time, it is definitely not invariant. T prime is t minus vx by c square divided by root over of 1 minus v square over c square. X prime is equals to x minus vt divided by root over of 1 minus v square by c square. Y prime is equals to y, and z prime is equals to z. Now if you, these are the equations. Now what you can do is 1, 2, 3 and 4. You just multiply the first equation by c. You just multiply the first equation by c, then you get ct prime is equal to ct minus v by c times x whole thing divided by root over of 1 minus v square by c square. X prime is equal to x minus, you just do the same thing here, v by c, and you make this as ct because ct is the coordinate, 1 minus v square by c square. Y prime is equals to y, and z prime is equal to z. Now basically what is ct prime? Ct prime is, this is actually x0 prime, this is x1 prime, right? This is x2 prime, and this is x3 prime. So these are the, this is the thing, and here you can write it like this. In short, we usually take b by c is equal to beta and root over 1 minus v square by c square is equals to gamma. Gamma is basically a function of beta, so that you know. So if you plug this in here, you get x0 minus beta x1 times gamma. Okay, this should be equal. Just a second, you can light it properly. So this is x0 minus beta x times gamma. This is beta x1, right, times gamma. This should be x1 minus beta x0 times gamma, and this is actually x2 and this is actually x3. Now you can easily write this in the matrix form. So in matrix form should look like this. Here you have the prime, x0 prime, x1 prime, x2 prime, x3 prime, and you have the Lorentz transformation matrix here. Just plug this value in. You have the gamma here. See, gamma minus beta gamma 0 0, then you have minus beta gamma 0 0, then you have the 0 0 1 0 0 0 0 1 times the column vector. x0, this is unprimed column vector, x1, x2 and x3. Okay, so this is the Lorentz transformation matrix. This is denoted as L mu nu, and this is actually x mu and this is x nu. So if you write it in a tensorial form, it looks like this. If you write it in a tensorial form, it looks like this. Just a second. Yes, if you write it in a tensorial form, L mu nu x nu. Fine. C nu is contracted and you get the x mu. So this is the Lorentz transformation, and this transformation matrix transforms from the unprimed coordinate, the event in an unprimed coordinate, to a event in a prime coordinate. So this is, Now in this lecture we are interested in writing down the equation which is invariant under this Lorentz transformation. Classically, Maxwell's equations are invariant under Lorentz transformations. Now one thing I want to tell you that Schrodinger's equation is not invariant under Lorentz transformation. So we need to seek for equations which is invariant under Lorentz transformation. Now let me write down the Schrodinger's equation for a particle moving in an electromagnetic field. This is the equation which needs to be replaced. So let me write down the equation, the Schrodinger's equation. equation of a particle of mass m and charge q in an EM field described by the scalar potential V RT. So V is the scalar potential which is a function of space and time, and the vector potential A RT. Fine. So the Schrodinger's equation looks like this: I h cut del del t of psi RT is equal to 1 by 2m h cut by I del minus q by c A RT whole square plus q times v function of RT operating on psi RT. So this is the Schrodinger's equation in a non-relativistic case, and this equation needs to be replaced, and that will lead to some very important consequences. The representation of psi will be no longer a single dimension 1, but it will be of dimension greater than 1, and that will represent spin along with its particle and antiparticle. Now let's directly go to the Klein Gordon equation to start with. So Klein Gordon equation. This is an equation which is invariant under Lorentz transformation. Now in the Klein Gordon equation, what Klein Gordon did is he took the dispersion relation. We know the dispersion relation for the free particle. E square is equals to P square C square plus M square C4, and he replaced this E and P by the corresponding operators. Okay, before going into that, let me tell you something. Once this dispersion relation is taken, E is immediately plus minus root over of P square C square plus M square C4. Now if this as far as this positive energy is concerned, we don't have a problem. People are used to positive energies, but as far as this negative energy is concerned, this negative energy makes the system unstable, because if P increases, energy decreases, so the particle will radiate energy and the system becomes unstable. So that was arrested by the particle antiparticle theory. The particles are having the positive energies and the antiparticles are having the negative energies, so this instability got arrested. Now let's start with the Klein Gordon equation. E is replaced by I h cut del del t. So this is, that means which is the energy operator, and P goes to, and then I'm taking the vector minus I h cut del. This is the E vector operator. Now in this relation, E and P are replaced by operators and they are allowed to operate on a wave function psi. So what we get is minus h car square del 2 psi, which is a function of space and time RT. Del 2 psi del T2 is equal to minus h car square, there is a c square, del square psi RT plus m square c to the power 4 psi RT. Now if we bring everything on the right hand side and divide by 1 by h car square c square, so that means minus 1 by h car square c square. If we divide by this, bringing everything on the left hand side, we get minus is already taken care of, so it's 1 by c square del 2 psi RT del T2 minus del square psi RT, okay, minus del square psi RT plus mc by h cut whole square psi RT is equal to 0. Now you see that this is the D'Alembert operator operating on psi. So it's 1 by c square del 2 del T2 minus del square operating on psi RT plus mc by h cut whole square psi RT. This is equal to 0. Now I told you in the first lecture, or also while doing on tensors, that this thing is represented by del mu plus mc by h cut whole square operating on psi, which is a function of space and time, is equals to 0. Now this is the Klein Gordon equation. You see that del mu is a operating on psi, it's a scalar, and mc by h cut whole square is also a scalar. One thing I need to point is the Compton wavelength h cut by mc, right? The Compton wavelength is h cut by mc, so we immediately see that this scale of Compton wavelength coming in the equation of Klein Gordon. So this is a relativistic equation. Okay, so del mu plus mc by h cut whole square operating on psi RT is equal to 0. This is the Klein Gordon equation, and this is invariant. Under Lorentz transformation. Okay, so this is invariant under Lorentz transformation. Now in natural units, if h cut is equal to c equal to 1 and box, you know, it's del mu, so this equation del mu plus m square psi is equal to 0. This is the Klein Gordon equation in natural units. In natural units, energy, momentum, mass, length inverse, time have the same dimensions. Now you can anytime retrieve these units by dimension analysis. Now what we shall do now is the current 4 vector associated with the Klein Gordon equation. So current 4 vector associated with Klein Gordon equation. Now what we do is we take the Klein Gordon equation and we multiply by psi star from the left, and we just subtract the same thing by swapping the stars. I do it immediately. So I do this keeping all the units intact. So psi star, I tell you this psi star or psi, these are functions of space and time, multiplied by the kg equation minus psi multiplied by the kg equation star. Now this must be equal to 0 because the itself kg equations are equal to 0. Now if I expand this, psi star box mc by h cut whole square operating on psi minus psi box plus mc by h cut whole square operating on psi star, this is equal to 0. Now just expand this. Psi star del mu plus psi plus mc by h cut whole square psi star psi minus psi del mu operating on psi star minus mc by h cut whole square multiplied by psi star equal to 0. Now see, you immediately see that mc by h cut whole square psi star psi and mc by h cut whole square psi star cancels because these are the same thing, and since psi and psi star can be swapped, so these are the same thing. So this is equal to now let me expand this del mu. So this psi star 1 by c square del 2 psi del t2 minus del square psi minus psi 1 by c square del 2 psi star del t2 minus del square psi star is equal to 0. Now let's collect the time and space part separately. So psi star, so 1 by c square is outside, del 2 psi del t2 minus psi del 2 psi star del t2 minus psi del square psi star minus psi star oh sorry this will be star and this will be unstarred. Okay, no point in giving a vector, it's a Laplacian operator, sorry. Del square psi star equal to 0. Now I can write this as, and what I do is I replace this minus sign by 1 by I square. There is a reason. Actually I am doing this looking into the current probability current density which we got in the Schrodinger's equation. So that I shall keep on in the second term, but I shall see that the first term, the rho will change, right? What we got rho in Schrodinger's equation, we got rho as psi star psi, but this time it will not be psi star psi. Let's see what we get. So this is del t so 1 by c square psi star. So just a second. Keep 1 by c square outside first. Del t of psi star del psi del t minus del t minus, this will be divergence of, let me replace this by 1 by I square plus 1 by I square, I is root of minus 1, and this is divergence of psi star grad psi minus psi grad psi star. This is equals to 0. See, from this term I get a two terms like this, del psi dot del psi star here, and this term, and here we get a this first term from the first term we get this, and the second term we get this. Now these two gets cancelled, right? These are the two terms which I am getting after taking this divergence of this vector. So these two terms gets cancelled. So you understand this. And what we get is this first term we get. Now, now what is J in Schrodinger's equation, the probability current density? J is h cross by 2im. So I think you remember J in Schrodinger's equation, this S stands for Schrodinger's, h cross by 2im psi star grad psi minus psi grad psi star. So if I want to bring this, I is already there, so h cross by, I must multiply by h cross by I h cross by 2m. So multiply by I h cross by twice m. So multiply the whole equation by I h cross by twice m and allow this c square to get in. So what we get is del t of I h cut by twice m c square, right? And then we have a psi star del psi del t minus psi del psi star del t plus we have the divergence of h cut by 2im psi star grad psi minus psi grad psi star. This is equal to 0. See, this term, the second term, we get this j, right? Now, since this we have obtained from Klein Gordon equation, we just keep a suffix as Klein Gordon. But this is very similar to what we got in Schrodinger's equation. Now see what we get on the left hand side. The left hand side means, sorry, the first term. The first term we have rho. So this is rho. This is rho. So rho Klein Gordon is this, right? No need to write it again. So the rho changes. Rho changes in case of Klein Gordon equation. What you got in Schrodinger's equation, I think you still remember. Rho for Schrodinger's is psi star psi, and this is, what does this represent? This represents the probability current density. But rho in Klein Gordon must be interpreted in a different way. This is not the probability current density. Keep this in mind. So in Klein Gordon equation we have to interpret in a different way. So this is for Schrodinger's and this is for the Klein Gordon. So what the Klein Gordon equation, continuity equation for the Klein Gordon looks like, this is also called the charge conservation. That is what I want to tell you. And so this is del, sorry, okay, you can keep this del, it's not a problem. Del is for the j, del rho del t dot rho for Klein Gordon dot del plus del dot j Klein Gordon is equal to 0. This equation is called the charge conservation. Where rho kg is equal to you see I h cut by twice m c square, I h cut by twice m c square psi star del psi del t minus psi del psi star del t. Psi is definitely a function of time. Now this is not equal to rho Schrodinger's, which is psi star psi, but j Klein Gordon is equals to h cross by twice I m psi star grad psi minus psi grad psi star, which is equal to j Schrodinger. Now in case of Schrodinger's equation, the rho represents this is the probability current density, oh sorry, this is the probability density, which is greater than 0. But so let me write it explicitly. For Schrodinger's equation, rho s is greater than 0 which represents the probability current density but in case of Klein Gordon equation, rho Klein Gordon is real but not positive definite. You can have a negative rho as well, so that has to be interpreted properly. And rho and also rho represent the charge density. Now if you want to write J mu in the covariant form, J mu will be rho c, this is the time component and this is the space component 3 vector. So that is I h cut by twice m psi star del psi del x mu minus psi del psi star del x mu, and the current conservation equation, this current conservation charge conservation equation looks like this. Del mu J mu is equal to 0. So this is invariant under Lorentz transformation. So this charge conservation is invariant under Lorentz transformation. Okay. Now, if you want to, so this is the continuity equation. Or charge conservation. Now you can do one thing, you can integrate this equation through all space, make a volume integral and through all space and allow this current density to vanish at infinity. Then it looks somewhat like this. Let's take this integration del, just a second. So del rho del t, I'm talking of this Klein Gordon rho, plus del dot j equals to 0. Now if you integrate this whole equation, through space, you get it like this. So this is equal to 0. So the first term will be del t of the volume integral plus, naturally you can change it to dq ddt, because this integration is a definite integral, and this integral over space is done. Now in the second part, what you can do is you can change this to surface integral by Gauss theorem. So if this is a surface integral, so this is j dot ds is equal to 0. Now if you define this quantity as q, this is the total charge, so then it will be dq dt, and this is equal to 0 since current vanishes at infinity. So this will imply that dq dt is equal to 0. So this is an immediate consequence of the charge conservation equation. Okay, now let's go to the solution for Klein Gordon equation in case of stationary states, and see what's the value of rho. Okay, what's the value of rho? Solution for stationary state wave function is psi equals to e to the power minus I et by h cut, some function of space. Now if you plug this in to the value of rho, so what is rho? Let's check. Rho Klein Gordon is this, right? So I h cut by twice mc square. So rho Klein Gordon is I h cut by twice m c square psi star del psi del t minus psi del psi star del t. If you plug this in here, you get E by mc square psi star psi. Now see, this looks like the Klein Gordon, Schrodinger's rho, except for this factor E by mc square. Right. Now for non-relativistic particles, E is approximately equal to mc square, and you get the Schrodinger's rho. So for non-relativistic particles where E is approximately equal to mc square, rho kg, rho Klein Gordon is rho Schrodinger's. Okay, now for relativistic particles, for relativistic particles, you have a Lorentz contraction. There is Lorentz contraction of volume by factor by E by mc square. Now what happens is, in this integral q is integral of rho dv. So this volume is contracted by the factor E by mc square, but this density increases by a factor of E by mc square, and this q remains invariant. So the q is invariant because rho increases by the factor E by mc square, while volume contracts by the same factor. This happens